Right, today I'm going to look at voltage, current, and resistance. I'm going to use um, a I'm going to use a simulation. So I'm going to show you how to find it. PHET. Um, and then you get these ones here. This is the website, and you got a few. They have lots and lots and lots of simulations. And most of the simulations I use are all from here. But in that case, we had the one that we've used this one before. But we're going to this time actually not use that one. I'm going to use. Let's go to here. Search circuits. We've got some simulation. We've got some activities we're going to use to go to the simulations. I'm going to pick on this one here. We've got a few different simulations here. I'm going to pick the one that allows me to play around with AC as well as DC. So, okay. So what we're going to do first of all. I mean, probably today we're going to be mainly looking at DC, direct current. We're going to be mainly understanding what is voltage, current, and resistance. So I'm going to start off by making a circuit. I might pause the video just to get a couple of circuits ready. Okay, so we've got two circuits here. We've got a switch in each one. The one on the left, as you can see, we've got two light bulbs. The one on the right, we have one light bulb. Now, I just realised I haven't picked the best simulation. There is a few different versions of this simulation. In this case, you got this ammeter, and this is kind of a bit more realistic because you would have to, of course, wire in the ammeter. So if I disconnect that, I guess it doesn't take that long actually. Just reconnect it like that. Currently it says 0 amps. Let's zoom in a little bit so we can read this a bit more easily. Oh, okay. Okay, maybe I'll have to zoom out then. All right, so we've got so that says 0 amps. Hopefully you can read that. If I close the switch, it now says 0.9 amps, and we have a light bulb lit up. These things moving around the circuit, you may know, are electrons. And let's compare it to the one on the left. And again, we have electrons moving around here. Let's look at making a bit of an observation. To my eye, it looks like the electrons are moving more quickly the one on the right compared to the one on the left. We can see if we just hold our cursor over one of them, it takes a little while for the electrons to pass by one electron to pass by, then the next one. We could even measure this with a stopwatch. I'm not going to bother doing it, but you could if you like. You can see how long it takes for one electron to come and then the next one. Meanwhile, if I do the same here, definitely looks to me like they're happening a lot more quickly. And you could, on the video, you could actually use the stopwatch there to see how long it takes, or you use your own stopwatch. Anyway, let's come over to the light bulbs now. We notice that the light bulbs are not as bright as they are on the one on the right. So why might this be? Well, the electrons have to do a certain amount of work. They use up a certain amount of energy going through the light bulbs, and they're going to have to go through one light bulb and then another. So they're kind of conserving their energy so as they can use it in each light bulb. In this case, all the energy can be used up all in one light bulb, and so that's basically what they do. So meanwhile, the battery is where they get the energy from in the first place. So essentially, as the electrons go through the battery, they collect a lot of energy. They go around the circuit, they use half the energy up in this light bulb, half the energy up in this light bulb. It's not necessarily always going to be half-half, because some light bulbs are easier to pass through than others, and this is where the idea of resistance comes from. So if I click on just one of them, so it's down here, resistance 10 ohms. So this would be the unit of resistance. We can measure resistance in ohms. So just briefly then, shall we talk about what resistance is? It's just for now, let's say it's the how difficult it is for electron to flow through a particular device. So if this device has a high resistance, it is difficult for the electrons to flow through it. If it has a low resistance, it's easy for the electrons to flow through it. So I'm going to break up this circuit here. I'm going to get another ammeter. I'm going to measure the current. While I'm doing that, you may want to make a prediction about what do you think the current's going to be. Might want to pause it if you want to have a think about that. It's 0.45 amps. So why is it 0.45 amps? Because the electrons are moving more slowly, but more accurately, more specifically, it's moving half as fast. Okay, it's moving twice as slow. And that's again because they're having to do twice as much work. So it's each time we have some resistance here, it's going to slow down the current. Now we have identical batteries there, so we can measure the voltage of the battery, which should essentially, for now, we can imagine it being the amount of energy we are giving the battery, the electrons. So, and I'll summarize this all up in notes in a moment. So don't worry about trying to remember all of this, but I'll just recap briefly here. We said the resistance was how difficult it is for the electrons to flow. They haven't talked about much about exactly what current is yet, but it's, I suppose I've sort of suggested it's how quickly the electrons are flowing. That's more or less correct. And then the voltage, more or less, is the amount of energy the electrons are given or the amount of energy that they lose. So if I've used this red electrode for before, as the electrons go from the red to the black one. So I'm going to do the same with the light bulbs. So let's start off with, let's do the right hand one first actually. So there's before, there's after, and 9 volts. And now what happens as it goes to the light bulb? There's before, there's after, minus 9 volts. So the minus is just saying that it's lost that much energy. Generally speaking, the plus or minus voltage is kind of ignored. We might write down 9-volt battery, 9 volt across the light bulb. But the reason why I'm deliberately doing it in a particular order, so as to get a negative 9 volts, is just to kind of emphasize a key point about what the about the voltage. So it's the amount of energy that's gained across the battery, but then it's the amount of energy lost across the light bulb. So we saw already that was 9 volts as well. We're going to do the red before, black afterwards again for both light bulbs, and again it's minus 9 volts. If we just did red before and black after the first light bulb, it's 4.5 or negative 4.5 volts. So it's lost half of the voltage, or as I said, half of the energy across the first one. And if we take the red one and go before the second one, black after the second one, and another 4.5 volts there. And again, like I said, in total, 9 volts across both of them. So let's. What I'll do is I'm going to take a snapshot of. I'm just going to put this away. Actually, I'm going to take a snapshot of this and link the image. Add a link to the image so you can play around this yourself, and I'll make a few notes on the whiteboard, and then we'll quickly go through them. Okay, I'll just pause the video. Okay, so let's have a quick think about this then. So what were our observations? I've got circuit A, got circuit B. So we can say that circuit A, or maybe let's say the current, make this a bit wider. The current in circuit A was lower. In fact, we can be more specific, and that was half of that in circuit B. We can say the electrons were moving more slowly in circuit A. We'll probably find out if we were able to measure it accurately. We'd probably find out they were moving half as fast, but we didn't measure that. But we could see by eye that they were moving certainly slower. We can see also that we also saw both circuits had the same voltage battery. The voltage they gained. There was a positive voltage across the battery and a negative voltage across the light bulbs. And in circuit A, the voltage was shared across the two light bulbs. Okay, and okay, that's those are the observations. Now let's try to define some of these different words that we've used. So current. Now I'll give this green. Make this green. So we saw that it's. We started off by saying it's how quickly the electrons are moving, but be a bit more precise than that. It doesn't have to be electrons that are carrying the current. It just needs to be anything that has a charge. So we'll talk about what a charge is in a moment, but yeah, I'll talk about that. Maybe I should have talked about that first, but no, it's okay. We'll talk about current first. So electrons have a charge. So do lots of things you may already know about charge a little bit, like protons have a charge and so on. If something has a charge and it is moving, then we can say charge is moving. Okay, or we can say the things that are moving are carrying the charge. So we can call those things charge carriers. But so current is really it is the textbook definition would be the rate of flow of charge. So the rate, well, that just means how often, how quickly, it's to do with speed, how much charge is flowing by per second. So it's the charge per second. So the electrons if the electrons are moving more quickly, then we would have a higher current because more charge would be passing by a point per second. However, it is possible that there is just more electrons moving at the same time, and in that case, the current is still higher. So, in other words, the words, a lot of the words in electricity are kind of metaphors for water. So we've heard the word. You've probably heard of a water current, a river current, or an ocean current, and so they do that quite a few times. So if we imagine like a river, we can think of the current in a river as the volume, maybe not that colour, volume of water. Let's say current. I'm not saying this is the only way to think about current in water, but just in this analogy, the volume of water per second. So what volume of water passes by a point in every second? If we had like a tap down here, how quickly could we fill a bucket of water, I guess? So in this case, we can say this is quite a wide river, maybe quite a deep river. So the water could be flowing quite slowly, but there's so much of it flowing at the same time that we could say that it's a high current. And then if it comes down here into, let's get rid of the outline, I think. And then if it suddenly reaches a really small bit there, in order for it to have the same volume of water per second, the water would now have to move a lot more quickly. And this is the same in the case of wires in electricity. So the electrons, if it's a really wide wire, then a really thick wire, the electrons don't have to move as quickly to get such a high current. And if it's a thin wire, they would have to move a lot more quickly to produce a high current, to produce the same size current. So if we have, so what was I saying? Hang on a second. So basically, current is, as I say, the rate of flow of charge as opposed to the speed at which the electrons are moving. If the electrons are moving faster, then the current is going to increase, but that's not the only way of increasing the current. You could just have more electrons moving at any one time, and also it doesn't need to be electrons. It could just needs to be anything that has a charge, but most of the time it's electrons. What do we measure? What do we measure current in? So we measure current in amps. What do we measure it with? With an ammeter. And so we measure it in amps with an ammeter. And as you can see in this diagram, we've had to put the ammeter in the circuit. So we can say it's in series. So it's the one thing after another. Okay. But in both of these circuits, we could say everything is in series. We'll explain what the opposite of being in series is in a moment, like in parallel. But everything is in one loop. Okay, there's no branching off. The wires don't branch off to another route. So we say it's in series. So we'll say measure in series. In fact, maybe I should say, let's add a new sentence. The ammeter must be wired in series. Now, another thing we can say here is, because it's the rate of flow of charge, the amount of charge per second, then you can actually work it out using a formula. So current, it's a bit messy. Okay. Current is equal to the amount of charge passing by a point divided by the amount of time. Okay, let's before we look at voltage and resistance, let's talk about what charge is then. So I'll just make a new word box and maybe a different color. Maybe that. Okay, so we've got charge. Well, there's not much to say about charge actually, other than we don't really know much about charge, other than some things, or let's say some particles. Let's try that again. Particles have charge, and some do not. For example, electrons have a charge. Now, so we can call electrons, and I mentioned this earlier on, charge carriers. I'm just going to squash this. And what do we measure charge with? Well, what do we measure it in? In other words, the unit. We measure charge in coulombs. Not sure I think you measured charge with the coulomb meter, but It's not really something we'd talk about much at GCSE, so we'll ignore that for now. So they're charge carriers. Another thing I want to talk about is we do know other things about charge. We also know that you can have opposite charges. So we label these charges as positive and negative, and we can say opposite charges attract like charges. What do I mean by like charges? I mean positive and positive, or negative and negative. We don't say identical because one could be large, one could be small, but they're like, and so they're both positive or they're both negative. Like charges repel. So two electrons next to one another would repel each other, and then an electron and a proton would be attracted to one another. So, okay, so now this, but up here might make a little bit more sense. We know a little bit more about what charge is. I'm going to draw a quick diagram, in fact. So, we'll get a couple of protons. Okay, so there's one proton and there's another proton. I'll move this to one side, and they are going to repel. So we'll just get a couple of arrows just to say that they're repelling one another. Might make that a bit thicker. All right. Yeah. Okay. Oh, okay. Make it a little bit thicker. Oh, why isn't it frustrating? Okay, that'll do. So they really actually I want it to be exactly the same because it's I want you to know that they would repel with exactly the same size. There we go. Size force. So we've got current, we've got charge, and then we've got voltage. We want to do voltage and resistance. So one of the things, we'll start off by just doing a little bit of defining of resistance. So, and then we'll maybe come back a little bit later on. So resistance is a measure of how difficult it is for current to flow through that component. So components have a certain resistance. Different components have different resistances. So if it has a high resistance, it's hard for. So if a light bulb has a high resistance, it means it's hard for the current to flow through it. And current is measured. Put this on a new line. It's measured in ohms. Okay, we'll come back to that one a little bit, add a bit more to it in a moment. Let's look at voltage now. And I'll do that in this color, this kind of blue color. So voltage. We said that it's like the energy that the charge is being given, or the energy the electrons are being given. And so now I can be a bit more precise. It is so. In fact, let's do it like this. Voltage is Voltage is the energy per charge. However, we'll notice that we measured voltage in parallel. We always did it before and after. So the reason for that is because you're not quite measuring the energy per charge. you're measuring the change in energy per charge between 2 points. So that's why we do it. That's why we have one before and afterwards. We're looking at the change in energy per charge between 2 points. And so it's voltage. Voltage is measured in volts using a voltmeter. And the voltmeter is wired in parallel. So that just means it's not in the circuit like the current is, but it's like it's connected one wire before, one wire after, whatever it is that you're measuring. So it's measured with a voltmeter in parallel. Now we can get a definition here. Not a definition. Sorry, we've got a definition now. We want a formula. So if it's the energy per charge, then we can say volt. Whenever you see the word per, we can imagine that means divide. So voltage is equal to the energy, or let's say the energy change. Yeah, let's say energy change then. Change in energy. Energy change divided by charge. So that's the unit. That's the equation that kind of defines what voltage is. Let's group this as well. So when we're measuring the voltage, we're looking at the amount of energy the battery has given it, or the amount of energy per charge. Sorry, the battery's given it, or we're looking at the amount of energy the light bulb has used up per charge. So now coming back to resistance, then we can actually say that 1 ohm is so again, if a component has a resistance of 1 ohm, it would require a voltage of, don't seem to be able to type today, of 1 volt to produce a current of 1 amp. Okay, so that gives a more precise definition, and now we can see that therefore an ohm must be 1 volt per amp. And so we can say that a way of sort of defining resistance now with a formula is it's the voltage divided by the current. Okay, I'm going to carry on writing the words in a moment as opposed to symbols, and I'll introduce the symbols afterwards. So resistance is equal to voltage divided by current. Okay, so now we have, so what have we got? We've got a definition and understanding of current, resistance, charge, and voltage. We've got 3 formulae, a charge for an equation or formula equation, they're the same thing, for current, and 1 for voltage, and 1 for resistance. So where can we go from here? Okay, yeah. So let's do a table now to look at the units and everything like that. We've already talked about the units a little bit, but we'll just kind of summarize it in a table, I think. Yeah. So we'll put this over here. We'll just, it's already, okay, let's make it like that. And we'll make the text a bit bigger. Move it up like that. And then so the first one will just, I'm not sure what to call that, but these ones are going to be voltage. Okay. Okay, fine. Current, resistance, and charge. And what do we want to know about these things? Well, first of all, let's say what is the symbol for these different things? So we could, rather than writing the whole word, we could just, for example, for voltage, rather than writing the whole word, we could just write a capital V, because that's the symbol for voltage. I think I might make all this align to the center. Yeah, there we go. And I'm going to make the top row bold and color it in like that. Yeah, okay. So that's the symbol for voltage. And then we've got the unit for voltage, which is volt. And then we've got the unit symbol. This means what could I write instead of writing the unit? So instead of writing 5 volts, what could I write instead? What could I write instead of writing the whole word volt? And the symbol for volt is also a capital V. What's the symbol for current? Strangely enough, a capital I. Now that looks like a bit like an L, doesn't it? So I'm going to pick, let's pick that one. Hopefully you can see now that looks like an I want to make sure that you can see very easily that it is an I, capital I. And the symbol, the unit is an amp. The unit symbol, the symbol for an amp is a capital A. Resistance can be represented by a capital R, and it's measured in ohms. And the symbol for an ohm is actually a Greek letter called omega. I'm going to go and get it. Okay, there we go. That's the symbol for omega. The symbol for a charge is Q. The unit for a charge is coulomb. And the symbol for coulomb is capital C. So don't confuse this fourth column with the second column. The second column is what we would write instead of this word, and the fourth column is what we would write instead of this word. So, for example, I could say, if I say something like current, that I'm measuring current, and I see that it's 5 amps, then instead of writing that, I could write I instead of current, 5, instead of writing, so amps, and instead of writing amps, I could write just capital A. Now, voltage could be a bit confusing, because if I say voltage is equal to 10 volts, instead of writing voltage, I write a capital V. Instead of writing volts, I write a capital V. Now this whole thing here looks a little bit confusing if you know anything about algebra, because that V and that V is not the same V, right? Because how can V be equal to 10V? So just beware, just make sure not to get caught out by that. And so I think that's pretty much it for current, voltage, resistance, and charge.